now we will discuss the Aristotle's theory. Okay, it was actually a fallacy. Keep that in mind. He tried to answer it, but the theory he gave was completely incorrect. He tried to answer this very question. He said that suppose we have a ground, and over it a ball is laid down. We apply force onto this ball, say a body A. It will be displaced by some distance, okay? But it's a common observation, it's a common sense that with respect to time, at some instant of time, it will come to rest. So velocity will be 0. So Aristotle thought that there is some kind of tiredness. This body gets tired. This body gets tired as the time passes, okay? So he thought that like the human beings, if they work with respect to time, with the passage of time, human body or human beings, they need a rest. They come into rest because they are tired. And similarly, all the objects in the universe, in the physical world, they come to rest because they get tired. It was Aristotelian view, and it was common observation, and at that time it was well known, and it was famous among all the thinkers of the physical world which were dealing with these kind of stuff, okay? We can say physics. But this was a fallacy. He said that the bodies, like human beings, they get tired. So he suggested that if a body is kept in motion, if we want to keep a body in motion, to keep a body in motion, what kind of motion? It's uniform motion. The fallacy comes here, the uniform motion, because I already told you that if the body is in non-uniform motion, then certainly we need a force behind that, because to change velocity we need a push, we need a pull, we need some external agency, which is the force here, to keep accelerating. But in case of the uniform motion, with the velocity is kept constant, Aristotle said that as the body gets tired, so we need external force. To keep a body in motion, we need an external force to keep the body moving on, okay? So Aristotle gave the theory that an external force is required for every body to keep that body in uniform motion, but that was wrong, completely rejected. That's the Aristotelian fallacy. Look what the fallacy is. This is a fallacy, okay? It was proved that this is a fallacy because today we know that it's completely wrong. Aristotle completely ignored what we today call that the friction force, but we call that friction. So it was well established of many years, many centuries, I can say, that Aristotle's theory was completely right, because as we know that if any body is set in motion with respect to time, at any instant of time, it comes to a halt, it comes to rest. But it was not because that it is tired, that's why it comes to rest. But the theory, the first person who proved that this is actually a fallacy, it was Galileo Galilei, the founding father of modern physics. Galileo Galilei. What he did, he did some experimentations over this very problem to solve this. He took an object like Aristotle took, but on an inclined plane. This is an inclined plane. A body is set here, okay? He set this body free, and we know under the effect of the gravity, every body which is at some inclination, which is at some inclination or at some height, it comes down. Similar effect happens to this very object. This comes down, and he observed that at the initial point, its velocity here, the velocity was 0. But this body is set free, it comes in motion, and here it comes in acceleration. So velocity changes from 0 to some velocity, say v. Say v is 10 meters per second, okay? So there is a change in the velocity, and we know the change in the velocity is called as acceleration. Keep that in mind. Acceleration is change in the velocity with respect to time, okay? Or we can represent it for shorter periods of time, for shorter instant of time. It is represented as dv by dt. This is the acceleration. You might be well aware about this relation. So he observed that if the body is set free, it comes in acceleration. Okay, it is accelerated. He did another experiment. In this case, inclination was reversed. He put a body here, okay, at this point. We know it can't climb uphill of its own. We need a push for that. He applied some force onto it, starting with velocity 0. He tried to push it, and it's got at the first instant of time when force is applied, that is at t is equal to 0, its velocity is v. When it is set in motion, before that it was in rest. When force is applied, it comes in motion with a uniform velocity at the first instant. I'm saying at the first instant of time, the velocity is v, okay? But as it climbs upwards, its velocity gets down, gets decreased, okay? Velocity gets decreased, and it reaches some point. At this point, velocity ultimately dies. Velocity comes to 0, okay? Then he concluded that the body is retarded, because first the velocity was some, say, 10 meters per second, but ultimately it dies out. So there was a kind of retardation which is opposite to the acceleration. So here retardation was observed. The body got retardation, okay? 2 experiments, one where acceleration is brought into existence, another experiment, here retardation was observed. Then with the same force he applied onto an object on a plane which is horizontal, okay? He applied same force, so the initial velocity here was velocity v. Say for example here it traveled the distance of 2 meters. Here, say for instance 2 meters same. But here, when he applied the force here, same force with the same velocity moving first at the first instant, he observed that with the passage of time, as it covers 2 meters, the body does not stop here as in the first case. It goes on and stops here. Why it stops here? There was a real reason behind it, but it doesn't stop here at the 2 meters per second, at the 2 meter distance, which was the case earlier, okay? It stopped later on after time is equal to say 60 seconds. Fine, traveling a distance of say 50 meters. So he observed that, he concluded that it was not the body which gets tired, because same body was here, same body was here, same body was here, okay? At the first instant, same body got accelerated. In the second case, it got retarded. So if the body gets tired itself, so why in the first case it get accelerated? Because it is getting more and more energy, as per the Aristotle theory, if it is considered to be true. It should have retarded. In this case also, and in this case also, but only here retardation is observed fast, okay? So he concluded that there are three types of motions. One is acceleration, which is the accelerated bodies observed in the accelerated bodies. Second one is retarded bodies, and third one is intermediate. Okay, intermediate. He further tried. He did another experiment. Furthermore, he took a bowl-shaped container and took the same ball here at some height h from the ground level. This is the ground level at some height h. Okay, he dropped it, but now onwards he kept in mind that this body, the container, is smooth surfaced. That is, he got an idea that the main reason behind that is not the tiredness of the object. It is something dealt with the surface, because here the surface was of one kind, here the surface was of another kind, here the surface was of another kind. So he took in consideration the nature of the surface. So for that, what he did, he made this smooth surface as much as possible. So he did an experiment. He dropped this down. It was possessing some velocity. It came here, and ultimately it came almost to the same height. Although there was a difference in height, but approximately we can say this is up to the same height, because he tried to smoothen the surface as much as possible. It is not 100% smooth, frictionless, 100% no way. So that's why I'm saying that it was approximately h. Say it is h. So he further did the experiment with the same ball, but now what he did, he made the surface of the bowl like this, stretched, a kind of stretching in the bowl, but at the same height. The ball was again dropped with the same velocity v. Okay, he observed that as far as this surface is smooth, the ball reaches the same height again. Wow, that's a kind of craziness. Now this was a jerk to the Aristotelian theory. If the distance is stretched here it was only this much of distance to cover by the body, but here it is almost the double. Okay, he stretched the distance and observed that almost the same height is observed here also. Same height, but distance right now is double. So he concluded that with the passage of time, if we do the experiment, say we do the experiment, so this very portion is kept is lowered right now onwards. He did another experiment. He put a surface like this on the first place. On one side it was at some height, but on the another side he tilted it down. Okay, like what I am trying to say, like he made a bowl, he made a container of this shape like this. So he dropped it down with the same height h. Okay, with the same height h, with the same velocity it is dropping down again. And when it dropped down with the same velocity, he concluded that as much as he tried to smoothen the surface, smooth surface, almost frictionless, because this was the main reason behind all that experimentations which were coming, which were actually falsifying the concept of Aristotle. Frictionless, almost. Okay, so when he dropped it down, he observed that the ball continuously moving. Okay, and he concluded that if we are able to make the surface frictionless, this was the main reason. Frictionless, the keyword in here, it is the frictionless. Then what he concluded, then the body will be in uniform motion forever. That is, it can travel a distance of infinite. This was the, I can say, this was a jerk and blow to the Aristotelian theory. So the main key factor here was the frictionless surface. For example, take the same bowl. If it is surface is rough, that's with very much higher friction. At the first instant, velocity is v, but as it goes down, it comes under the effect of the friction, and frictional force pulls it down, so retards it. So the maximum travel distance is this. But as the surface is made frictionless, smooth, and is dropped at some height h, it tries to cover the same distance. So Galileo Galilei, he suggested and he proposed a theory that it is all dependent upon the friction of the surface. As much as we lessen the friction force of the friction of this surface, the body keeps on moving. Okay, so for frictionless condition, the body can move up to the infinite distances. So that means we need not to possess, we need not to we can say exert some external force. We need no external force. We need no external force for a body to keep it in uniform motion. To keep it in uniform motion. That was the main statement of Galileo Galilei's theory. He said that no external force is required. A body keeps in moving with the uniform velocity as far as the surface is frictionless. So to keep a body in, suppose in the ideal situations, because in the day-to-day life we come across the friction. Okay, suppose the surface is frictionless. Galileo Galilei supposed that for any body to keep in, if a body is moving with some velocity, that is the uniform motion, that will continue to move in the space-time forever, and no external force is required for that. So we got an idea that the body with uniform motion does not require any external force. So this was an insight. Given, which was given by the Galileo Galilei, that had eluded Aristotle actually and his followers. He concluded that uniform motion, what Galileo Galilei did. Galileo Galilei. What he concluded: uniform motion is if it is contained by some body F, it does not require any external force. So that means it will continue to be in the uniform motion. Similar case happens with the body which is at rest. Suppose this body is at rest. If no external force is there, this body will stay at rest, will remain at rest forever. So Galileo Galilei said that uniform motion of a body is equivalent to saying that it is equivalent to the state of rest. Is equivalent to say that it is equal to the state of rest. That means in both the cases, if we want to change the uniform motion of a body, we need force to change it. We need a force to change it. That means, or for similar situation happens to the similar case happens with the rest state. If a body is at rest, we need some external force to change it. Okay. So what he concluded that if we have, I will write it down, if net external force is 0, that means no acceleration will be observed, that is, no external force will be there. A body at rest continues to remain at rest. Similarly, and a body in uniform motion continues to remain in its state. Okay, continues to move with uniform motion. Okay, with uniform velocity, I can say. So he concluded that if a body is at rest, it will remain forever until and unless compelled by some force. And if a body is in uniform motion, that means it is possessing some velocity, it will remain in the state of motion with the moving with the uniform velocity until and unless external force is applied to it. So it will resist any external change. So no change will be happening inside the body until and unless some external force is applied to it. So this state possessing this process, this property is called as the inertia. So inertia, we can say this is a resistance to change. Resistance to any change. For example, the body is at rest, it will remain at rest. It will try to resist it to change its state. For example, it's at rest, it will remain at rest. Similarly, the body is in motion, uniform motion, it will remain in the uniform motion, it will resist the outer changes. That property which is possessed by bodies, this property is called as inertia. And Galileo Galilei said that he gave a law, actually. This is called the Galileo's law of inertia. Galileo's law of inertia. That any body continues to remain in motion, continues to be in its original, continues to remain or to be in its original state. Fine. So this was the Galileo's law of inertia. That's if a body is in motion, uniform motion, it tries to remain always in the uniform motion. If it is at rest, it tries to remain at rest until and unless external force is applied to it to change it. Okay.